Alright, hello everyone, welcome back. I'm your friend in XO. Today we'll be in the learning of
Analytic geometry.
analytic geometry. The first concept that we are going to learn is called the distance. Well, it's just about a method of calculating the length between 2 points. They have a formula for it.
In this video, we're going to learn it is 3 squared plus delta y, y2 squared plus the x.
Okay, alright. When say the distance or the length between 2 points, what I mean is you could actually use this formula to calculate out. For example, if you get a point 1 and you get a point 2, then how can you get the distance between them? Well, you use this formula. And the theory about it is that we should have a look at this video.
In this video, we're going to learn how to take the distance between any 2 points in our xy coordinate plane. And what you're going to see, it's really just an application of the Pythagorean theorem. So let's start with an example. Let's say I have the point. I'll do it in a darker color so we can see it on the graph paper. Let's say I have the point 3, -4. So if I were to graph it, I'd go 1, 2, 3, and then I'd go down 4. 1, 2, 3, 4. Right there is 3, -4. And let's say I also have the point 6, 0. 6, 0. So 1, 2, 3, 4, 5, 6. And then there's no movement in the y direction. We're just sitting on the x-axis. The y coordinate is 0, so that's 6, 0. And what I want to figure out is the distance between these 2 points. How far is this blue point away from this orange point? And at first you're like, gee, Sal, I don't think I've ever seen anything about how to solve for a distance like this. And what are you even talking about? The Pythagorean theorem? I don't see a triangle there. And if you don't see a triangle, let me draw it for you. Let me draw the triangle. Let me draw this triangle right there, just like that. Let me actually do several colors here just to really. So there's our triangle. And you might immediately recognize this is a right triangle. This is a right angle right there. The base goes straight left to right. The right side goes straight up and down. So we're dealing with a right triangle. So if we could just figure out what the base length is and what this height is, we could use a Pythagorean theorem to figure out this long side, the side that is opposite the right angle, the hypotenuse. This right here, the distance is the hypotenuse of this right triangle. Let me write that down. The distance is equal to the hypotenuse of this right triangle. So let me draw it a little bit bigger. So this is the hypotenuse right there. And then we have the side on the right, the side that goes straight up and down. And then we have our base. Now, how do we figure out? Let's call this d for distance. That's the length of our hypotenuse. How do we figure out the lengths of this up and down side and the base side right here? So let's look at the base first. What is this distance? You could even count it on this graph paper. But here we're at x is equal to, let me do it in the green. Here we're at x is equal to 3. And here we're at x is equal to 6. Right? We're just moving straight right. This is the same distance as that distance right there. So to figure out that distance, it's literally the end x point. And you can actually go either way because you're going to square everything. So it doesn't matter if you get negative numbers. So it's going to be 6. It's going to be, the distance here is going to be 6 minus 3, right? 6 minus 3. That's this distance right here, which is equal to 3. So we figured out the base. And just to remind ourselves, that is equal to the change in x. That was equal to your finishing x minus your starting x. 6 minus 3. This is our delta x. Now, by the same exact line of reasoning, this height right here is going to be your change in y. That's going to be your change in y. Up here, you're at y is equal to 0. That's kind of where you finish. That's your higher y point. And over here, you're at y is equal to -4. So change in y is equal to 0 minus -4. I'm just taking the larger y value minus the smaller y value, the larger x value minus the smaller x value. But you're going to see we're going to square it in a second. So even if you did it the other way around, you get a negative number, but you still get the same answer. So this is equal to 4. So this side is equal to 4. You could even count it on the graph paper if you like. And this side is equal to 3. And now we can do the Pythagorean theorem. The Pythagorean.
All right. So far, as we know, or as we have learned from this video, basically the distance between 2 points is, what you do is to draw a right angle triangle, right? Then after that, you could do the Pythagorean theorem with it to calculate out this length of this side of length. Yeah, the dot x or the dot y is the difference between this point x value minus this point x value. Of course, we're gonna get the absolute value of it. Then this point y value minus this point y value. And when we get this side of length, and when we get this side of length, after that after we got the dot x and the dot y, we do the Pythagorean theorem. I guess that's quite easy to understand. Nothing fancy out there, but in China they will never tell you how the distance formula come from. Then let's get into the midpoint formula.
Let's say I have the point 3 comma negative 4. So that would be 1, 2, 3, and then down 4. 1, 2, 3, 4. So that's 3 comma negative 4. 3 comma negative 4. And I also had the point 6 comma 1. So 1, 2, 3, 4, 5, 6 comma 1. So just like that, 6 comma 1. In the last video, we figured out that we could just use the Pythagorean theorem if we wanted to figure out the distance between these 2 points. We just drew a triangle there and realized that this was the hypotenuse. In this video, we're going to try to figure out what is the coordinate of the point that is exactly halfway between this point and that point. So this right here is kind of the distance, the line that connects them. Now, what is the coordinate of the point that is exactly halfway in between the two? What is this coordinate right here? It's something comma something. And to do that, let me draw it really big here, because I think you're going to find out that it's actually pretty straightforward. At first, it seems like a really tough problem. Gee, let me use the distance formula with some variables. But you're going to see it's actually one of the simplest things you'll learn in algebra and geometry. So let's say that this is my triangle right there. That is my triangle right there. This right here is the point 6 comma 1. This down here is the point 3 comma negative 4. And we're looking for the point that is smack dab in between those 2 points. What are its coordinates? And it seems very hard at first. But it's easy when you think about it in terms of just the x and the y coordinates. What's this guy's x coordinate going to be? This out here, this line out here represents x is equal to 6. This over here, let me do it in a little darker color. This over here represents x is equal to 6. This over here represents x is equal to 3. What will this guy's x coordinate be? Well, he's going to be his x coordinate is going to be smack dab in between the two x coordinates. Right? This is x is equal to 3. This is x equal to 6. He's going to be right in between. This distance is going to be equal to that distance. His x coordinate is going to be right in between the 3 and the 6. So what do we call the number that's right in between?
All right, that's too much. I guess for this solution is quite simple, or we can easily get the result back. For example, if we want to get the midpoint x value, how do we do that? We draw a line here. All right, and for now, as you know, the x value, if you look at it carefully, it would be just equal to the point A's x value plus the point B's x value, then we divide it by 2. So we will get the midpoint's x value. And for the y value, it's almost the same thing. We just have to add the point A's y plus the point B's y, and then we divide it by 2. And we're done. So in the end, you may get some kind of formula like this. If you get 2 points, you divide the xy, you get the midpoint by using this formula right in here. That was kind of easy. Let's go on dividing line segments.
Find the point B on segment AC such that the ratio of AB to BC is 3 to 1. And I encourage you to pause this video and try this on your own. So let's think about what they're asking. So if that's point C, I'm just going to redraw this line segment just to conceptualize what they're asking for. And that's point A. They're asking us to find some point B, that the distance between C and B, so that's this distance right over here. So if this distance is x, then the distance between B and A is going to be 3 times that. It's going to be 3 times that. So this will be 3x. That the ratio of AB to BC is 3 to 1. So that would be the ratio. Let me write this down. It would be AB, that looks like an HB. It would be AB to BC is going to be equal to 3x to x, which is the same thing as 3 to 1, which is the same thing as 3 to 1, if we wanted to write it a slightly different way. So how can we think about it? You might be tempted to say, oh, well, you could use the distance formula to find the distance, which by itself isn't completely uncomplicated, and then this will be 1/4 of the way, because if you think about it, this entire distance is going to be 4x. This entire distance is going to be, let me draw that a little bit neater. This entire distance, if you have an x plus a 3x, is going to be 4x. So you'd say, well, this is 1 out of the 4x's along the way. This is going to be 1/4 of the distance between the 2 points. So this is, let me write that down. This is 1/4 of the way. 1/4 of the way between C and B. Going from C to A. B is going to be 1/4 of the way, so maybe you try to find the distance, and you say, oh, well, what are all the points that are 1/4 away? But it has to be 1/4 of that distance away, but then it has to be on that line. But that makes it complicated, because this line is at an incline. It's not just horizontal, it's not just vertical. What we can do, however, is break this problem down into the vertical part, the vertical change between A and C, and the horizontal change between A and C. So, for example, the horizontal change between A and C, A is at 9. A is at 9 right over here. And C is at -7. C is at -7. So this distance right over here is 9 minus -7. 9 minus -7, which is equal to 9 plus 7, which is equal to 16. And you see that here. 9 plus 7, this total distance is 16. That's the horizontal distance change going from A to C, or going from C to A. And the vertical change, and you could even just count that, that's going to be 4. C is at 1, A is at 5, going from 1 to 5, you've changed vertically 4. So what we can say, going from C to B in each direction, in the vertical direction and the horizontal direction, we're going to go 1/4 of the way. So if we go 1/4 in the vertical direction, we're going to end up at y is equal to 2. And if we go, so I'm just going, starting at C, 1/4 of the way. 1/4 of 4 is 1. So I've just moved up 1. So our y is going to be equal to 2. And if we go 1/4 in the horizontal direction, 1/4 of 16 is 4. So we go 1, 2, 3, 4. So we end up right over here. Our x is -3. So we end up at that point right over there. We end up at this point. This is the point -3, 2. And if you were really careful with your drawing, you could have actually just drawn, actually you don't have to be that careful since this is graph paper.
All right. So if you ask me how he did that, how he managed to solve out the position of the B, I guess, I would just say what he did is to get the ratio between the CB and BA. Then he do the same thing for the x axis and the y axis, because they have the same property. So if CB is a x and BA is a 3x, then that means if you move your A into here, and you will get a vertical line that represents the y axis. Then, if you move your B into here, you will generally notice that the length of B prime, say, is 1/4 of the prime AB, because they have the same property.
So the goal of this video is to prove that the three medians of a triangle always intersect at one point, which is pretty interesting because you would expect two different lines with different slopes to intersect in one point, but three lines intersecting in one point is pretty neat. And this is true for all triangles. And so to set up this proof, I've put an arbitrary triangle here, but I've put one vertex at the origin. That'll simplify the math. And then I put another vertex on the x-axis. And I've given them coordinates. So this one right over here is at 0, 0. This one over here, we're just saying that the x-coordinate is a, and so it's a, comma, 0. And then this one up here has some x and some y coordinate. We're just calling them b and c. This is some arbitrary triangle. And if you had some other triangle that had the same dimensions as this one, and this one can have any dimensions because we haven't defined a, b, and c, you could go from this triangle to any of those other ones using rigid transformations. So if we can prove that the medians of this triangle, this general triangle, always intersect at one point, this will be true for all triangles. So let's do a little bit more. Let's draw the medians. So what we're going to do is draw lines from each of the vertex to the midpoint of the opposite side. So if we do that, we've drawn all the medians, and it for sure looks like they intersect at one point. But to prove that, let's think about what the coordinates are of the midpoints of each of these sides. So what is the coordinate right over here? Pause this video and think about it. Well, this is going to be the midpoint of this top point and this bottom right point. So this length is equal to that length. And for the midpoint, you can really just think about it as you're taking the average of each of the coordinates. So the x-coordinate here is going to be the average of b and a. So you could just write that as a plus b over 2. And then the y-coordinate is going to be the average of c and 0. That would be c plus 0 over 2, or just c over 2. And we could do that for each of these points. So this point right over here, its x-coordinate is going to be the average of 0 and a. So that's just a over 2. And its y-coordinate is going to be the average of 0 and 0. You can see that it sits on the x-axis, so its y-coordinate is 0. And then last but not least, what's the coordinate of this point? Pause the video and try to figure that out. All right. Well, the x-coordinate is going to be the average of b and 0, which is just going to be b over 2. And then the y-coordinate is going to be the average of c and 0, which is just going to be c. The way that I'm going to prove that all three of these medians intersect at a unique point is by showing you a coordinate that sits on all three lines. If it sits on all three lines, that must be the point of intersection. And that interesting point is 2/3 along the way of any one of the medians. So one way to think about it is the distance between the vertex and that point is 2/3 of the length of the median. So if we just look at this blue median, the coordinate of this point that is twice as far away from the vertex as it is from the opposite side, it will be based on a weighted average of the x and y coordinates. When we did a midpoint and things were equally far away, you equally weighted the coordinates. So you just took their average. But if you are closer to this side, you will take a weighted average accordingly. So it's going to be 2/3 times a plus b over 2 plus 1/3 times 0. And then the y-coordinate is going to be 2/3 times c over 2 plus 1/3 times the y-coordinate here, which is just going to be 0. Now, once again, why do we have this 2/3 and this 1/3 weighting? Because we are twice as close to this point as we are to that point. Now, if we wanted to simplify it, what would we get? So this 2 would cancel with that 2, and this is 0, so we would get a plus b over 3 for the x-coordinate. And for the y-coordinate, this is 0. That 2 cancels with that 2, and we get c over 3. So we just found a point that for sure sits on this blue median. Now let's do a similar exercise with this pink colored. So that pink colored median, what is the coordinate of the point that sits on that median that is twice as far from the vertex as it is from the opposite side? Well, it would be the exact same exercise. we would doubly weight these coordinates. So the x-coordinate would be 2/3 times b over 2 plus 1/3 times a, 1/3 times a. And then the y-coordinate would be 2/3 times c over 2, 2/3 times c over 2, plus 1/3 times 0, 1/3 times 0. And what does that get us? Well, let's see. This 2 cancels out with that 2, and we are left with b over 3 plus a over 3. So that's the same thing as a plus b over 3. And over here, that's 0. That cancels out. That is c over 3. So notice, this exact coordinate sits on both the blue median and this pink median. So that must be the place.
Okay, I was kind of confusing about it. Oh, sorry, I was kind of confused about it. So I know where the 2/3 comes from. This represents the ratio of this line.
Place that they intersect. Let's see if that's.
But where's the b over 2? It's the x value for this point. Then what about the 1/3? Where is that comes from? Okay, I thought they would do that together, but it seems like it's doing it separately. So when you look at it, you get let's say this is one point and this is another point. They have some ratio between two line segments, and the ratio of this segment is 2/3, and the ratio for this segment is 1/3. What I did is for the points over here, I use the opposite line segment ratio, which is 1/3, and also for the zero, it's also used the ratio of 1/3. But for points in here, for example, the b over 3, what I used is the opposite line segment ratio, which is 2/3. That's kind of different. And for the 3/2, for this one, it's also using the opposite line segment ratio. I don't know why he do that, but that's it. It's probably in this video. I didn't watch it before.
Point A is at -1, 4, and point C is at 4, -6. Find the coordinates of point B on line segment AC such that the ratio of AB to AC is 3:5. So pause this video and see if you can figure it out. All right, now let's work through this together. And to help us visualize, let's plot these points. So first, let us plot point A, which is at -1, 4. So -1, 1, 2, 3, 4. So that right over there is point A. And then let's think about point C, which is at 4, -6. So 1, 2, 3, 4, -6. -1, -2, -3, -4, -5, -6. Just like that. And so the segment AC, I get my ruler tool out here, segment AC is going to look like that. And the ratio between the distance of A to B and A to C is 3:5. Or another way to think about it is B is going to be 3/5 along the way from A to C. Now the way that I think about it is, in order to be 3/5 along the way from A to C, you have to be 3/5 along the way in the X direction and 3/5 along the way in the Y direction. So let's think about the X direction first. We are going from X equals -1 to X equals 4 to go from this point to that point. Our change in X is 1, 2, 3, 4, 5. And so if we want to go 3/5 of that, we went a total of 5. 3/5 of that is going just 3. So that is going to be B's X coordinate. And then we can look on the Y coordinate side. To go from A to C, we are going from 4 to -6. So we're going down by 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And so 3/5 of 10 would be 6. So B's coordinate is going to be 1, 2, 3, 4, 5, 6 down. So just like that, we were able to figure out the x and the y coordinates for point B, which would be right over here. And you could look at this directly and say, look, B is going to have the coordinates. This looks like this is 2, comma, -2, which we were able to do with the graph paper. So another way you could think about it even algebraically is the coordinates of B, we could think about it as starting with the coordinates of A, so -1, comma 4. But we're going to move 3/5 along the way in each of these dimensions towards C. So it's going to be plus 3/5 times how far we've gone in the x direction. So in the x direction, to go from A to C, we're going from -1 to 4. And so that distance is 4 minus -1. And this, of course, is going to be equal to 5. And then on the y dimension, this is going to be our A's y coordinate plus 3/5 times the distance that we travel in the y direction. And here we're going from 4 to -6. So if we say -6 minus 4, that is -10. And so the coordinates of B are going to be -1 plus 3/5 times 5 is going to be plus 3. And then 4 plus 3/5 times -10. Well, 3/5 times -10 is -6. And so that gets us to comma -2. And we are done, which is exactly what we got right.
You know what, when I look at this graph, or when I look at the representation of the whole stuff, what I was thinking about, well, standing with those numbers alone doesn't make us more efficient or make us powerful. But when we convert those expressions or math formula into a program, yes, I said program, by using some programming technique, then we will be very powerful. We will get that power from it because since it's a software or since it's a executable code, we would be able to use it to process thousands or millions of data without human interpreted. You know, for human, he cannot do such a calculation in that fast speed and accuracy. But for computer, it's totally capable of doing that.
So we have a trapezoid here on the coordinate plane. And what we want to do is find the area of this trapezoid just given this diagram. And like always, pause this video and see if you can figure it out. Well, we know how to figure out the area of a trapezoid. We have videos where we derive this formula. But the area of a trapezoid, just put simply, is equal to the average of the lengths of the bases. We could say base 1 plus base 2 times the height. And so what are our bases here? And what is going to be our height over here? Well, we could call base 1, we could call that segment CL. So it would be the length of segment CL right over here. I'll do that in magenta. That is going to be base 1. Base 2, that could, let me do that in a different color. Base 2 would be the length of segment OW, or B2 would be the length of segment OW, right over there. And then our height H, well, that would just be an altitude. And they did one in a dotted line here. Notice it intersects the base 1, I guess you could say segment CL at a right angle here. And so this would be the height. So if we know the lengths of each of these, if we know each of these values, which are the lengths of these segments, then we can evaluate the area of this actual trapezoid. And once again, if this is completely unfamiliar to you, or if you're curious, we have multiple videos talking about the proofs or how we came up with this formula. You can even break down a trapezoid into 2 triangles and a rectangle, which is one way to think about it. But anyway, let's see how we could figure this out. So the first one is, what is B1 going to be? B1 is the length of segment CL. And you could say, well, look, we know what the coordinates of these points are. You could say, let's use the distance formula. And you could say, well, the distance formula is just an application of the Pythagorean theorem. So this is just going to be the square root of our change in x squared. So our change in x is going to be this right over here. And notice we're going from x equals -4 to x equals 8 as we go from C to L. So our change in x is equal to 8 minus negative 4, which is equal to 12. And our change in y, we're going from y equals negative 1 to y equals 5. So we could say our change in y is equal to 5 minus negative 1, which of course is equal to 6. And you see that here, 1, 2, 3, 4, 5, 6. And the segment that we care about, its length that we care about, that's just the hypotenuse of this right triangle that has one side 12 and one side 6. So the length of that hypotenuse from the Pythagorean theorem, and as I mentioned, the distance formula is just an application of the Pythagorean theorem. This is going to be our change in x squared, 12 squared, plus our change in y squared, so plus 6 squared. And this is going to be equal to 144 plus 36. So the square root of 144 plus 36 is 180, which is equal to, let's see, 180 is 36 times 5. So that is 6 square roots of 5. All right, let me not skip some steps. So this is the square root of 36 times 5, which is equal to, square root of 36 is 6. So 6 square roots of 5. Now let's figure out b2. So b2, once again, change in x squared plus the square root of change in x squared plus change in y squared. Well, let's see. If we're going from, we could set up a right triangle, if you like this, to figure those things out. So our change in x, we're going from x is at negative 2. X is going from negative 2 to positive 4. So our change in x is 6. Our change in y, we are going from y equals 5 to y equals 8. So our change in y is equal to 3. So just applying the Pythagorean theorem to find the length of the hypotenuse here, it's going to be the square root of change in x squared, 6 squared, plus change in y squared, plus 3 squared, which is going to be equal to, it's going to be equal to 36 plus 9, which is 45. So square root of 45, which is equal to the square root of 9 times 5, which is equal to 3 square roots of 5. And so we only have one left to figure out. We have to figure out h. We have to figure out the length of h. So h is going to be equal to, and so what is our, if we're going from w to n, our change in x is 2. Change in x is equal to 2. We're going from x equals 4 to x equals 6. If you wanted to do that purely numerically, you would say, okay, our end point, our x value is 6, our starting point, our x value is 4. 6 minus 4 is 2. You see that visually here. So it's going to be the square root of 2 squared plus our, let me write that radical a little bit better. So it's the square root of our change in x squared.
Sorry, I was just lost my focus on this video. It's probably not that so interesting to me for now. So let me do some search about the JavaScript, because actually we could use JavaScript to do some drawing, of course with programming. It's probably not be called drawing, but instead they would like to say it's an animation neighborhood. Well, the most used one is Anime.js, and to be honest, I like this framework because I also used it before. We'll get into it later. Alright, fine. Let's just use Anime.js. Yeah, before we get started, let's get into some examples to say how it may look like. Well, it seems like there has no limitations for it. For example, when you look at this graph, you would think, oh, if it can make such a graph, then it can make anything 2D-dimensional stuff. And then when you look at this graph, you would think that yeah, this is the normal use case for the animation. You just want to make your website be more attractive than static, than following all those static images. That would be boring. And once again, I guess this is more interesting than the whole mathematics concept. And let's say one way to think about the importance of mathematics is that you could use some concept of it to make some amazing graphs like this one. For example, this one, what he uses is a concept of, let me say, I almost forgot about the word.
Dilate.
Dilate or dilation. It uses the word dilation and probably shrinking or scale down, some kind of things like that. And it also uses the concept of mirror. You have to rotate this cell from one angle to another angle. And for the light, it's kind of like a rotation in a certain amount of angles. And for the whole graph, what I did is to move up and move down. Those are basic geometry concepts, but you have to know it first to be able to make such a graph. Alright, when you look at this animation, you may think, well, it's so complex. But it's not. It's just a result when you change multiple property of that object together. Then you get this kind of result. And if you think about it, if you think about it, first it changes the location or the coordinates of each small cube. For example, the translate x and translate y. It moves all of them from one position to another position. And then it did some rotation for those little cubes right in here, especially the z-axis. And then for controlling such an transformation, what it did is to add a delay property for this animate function, so that it could do such a transformation during a time length, or what do we say, time duration, right? And yes, when you look at this graph, you will say, oh, it's just amazing that you could say, or you could feel like the little circle is alive. Well, that's true, because anything that moves forever, to you would think that it's alive. So how they did that, how they make such an animation? Well, it's just as simple as first you define a series of movements from, for example, move the x coordinate of that object, move the y coordinate of that object, then do some kind of scale. After that, after you have defined a series of actions, then you set the loop equal to true. If the loop equal to true, then the actions will be executed again and again. So it would seem like that object is alive forever. Alright, back to our mathematics learning. Well, let's get into it.
We are asked, which of these lines are parallel? So parallel lines are lines that have the same slope, and they're different lines, so they never ever intersect. So we need to look for different lines that have the exact same slope. And lucky for us, all of these lines are in y equals mx plus b, or slope-intercept form. So you can really just look at these lines and figure out their slopes. The slope for line A, m is equal to 2. We see it right over there. For line B, our slope is equal to 3. So these two guys are not parallel. And I'll graph it in a second, and you'll see that. And then finally, for line C, I'll do it in purple, the slope is 2. So m is equal to 2. I don't know if that purple is too dark for you. But so line C and line A have the same slope, but they're different lines. They have different y-intercepts. So they're going to be parallel. And to see
alright. So here what you have heard about, here's a word that you heard about is called slope. So what is that? It's just a property that represents that belongs to a line, and it measures how slope or how much angle it would have if you interact it with the x coordinates. Oh, sorry, with the x-axis. This is the x-axis. So if the slope, if this value equal to 0, it will be just be the x-axis. If the slope is approaching to infinity value, then it must be a vertical line. And if for two lines they have the same slope, for example, if I define the slope of this line equal to 2, then if we have another line which also has the same slope, for example the 2, then I would just say the two lines are parallel. And I know you must know the meaning of parallel. That this is exactly an example of parallel lines.
See that? Let's actually graph all of these characters. So line A.
Yeah, it's kind of boring. Let's see what we can do from it. Let's get into the second video.
We have 3 lines, and we have to figure out which of the 3 are parallel. So line A, and it can't be parallel on its own, it has to be parallel to another of the 3 lines. So the equation for line A is y is equal to 3/4 x minus 4. Line B is 4y minus 20 is equal to negative 3x. And then line C is negative 3x plus 4y is equal to 40. So to figure out if any of these lines are parallel to any of the other lines, we just have to compare their slopes. If any of these if any two of these lines have the same slope and they're different lines, they have different y-intercepts, then they're going to be parallel. Now line A, it's very easy to figure out its slope. It's already in slope-intercept form. This is mx plus b. The slope is 3/4, and the y-intercept, which isn't as relevant when you're figuring out parallel lines, is negative 4. So let's see what the other characters' slopes are. This isn't in any kind of standard form. It's not in standard form, slope intercept, or point slope form. But let's see what the slope of this line is. So to get it into slope intercept form, which is really the easiest one to pick out the slope from, let's add 20 to both sides of this equation. So let's add 20 to both sides. The left-hand side, those cancel out. That was the whole point. You get 4y is equal to negative 3x plus 20. And now we can divide everything by 4. Divide everything by 4, just dividing both sides of this equation by 4. We are left with y is equal to negative 3/4 x plus 5. So in this case, y-intercept is 5, but most importantly, the slope is negative 3/4. So it's different than this guy. This is negative 3/4. This is positive 3/4. So these two guys definitely aren't parallel. Let's move on to this guy written in standard form.
All right. So it seems like for this approach or for this method, if we have to do a comparison for whether the two lines are parallel, we have to convert the equation from this form to this form. For some of you, you may think that this is very important for student to do some exercise about the equation transformation. But I think once you know how can you do that, if you do that's too much, you would feel like, well, what's the point of that? Why have to do that transformation over and over again, which doesn't make any real values to our world. Alright, so this is today's learning, and inside of this video we have learned about the concept of distance formula and the midpoint formula, and also how can we determine if two lines are parallel. Oh, probably I didn't tell you how to determine if two lines are perpendicular. Well, let me say it must be in somewhere.
We are asked which of these lines are perpendicular. And it has to be perpendicular to one of the other lines. You can't be just perpendicular by yourself. And perpendicular lines, just so you have a visualization for what perpendicular lines look like, two lines are perpendicular if they intersect at right angles. So if this is one line right there, a perpendicular line will look like this. A perpendicular line will intersect it, but it won't just be any intersection. It will intersect at right angles. It will intersect at right angles. So these two lines are perpendicular. Now, if two lines are perpendicular, if the slope of this orange line is m, so let's say its equation is y is equal to mx plus, well, let's say it's b1, so it's some y-intercept, then the equation of this yellow line, its slope is going to be the negative inverse of this guy. This guy right here is going to be y is equal to negative 1 over mx plus some other y-intercept. Or another way to think about it is if two lines are perpendicular, the product of their slopes is going to be negative 1. And so you could write that there. M times negative 1 over m, negative 1 over m, that's going to be, these two guys are going to cancel out. That's going to be equal to negative 1. So let's figure out the slopes of each of these lines and figure out if any of them are the negative inverse of any of the other ones. So line A, the slope is pretty easy to figure out. It's already in.
So he already told us if two lines are perpendicular, then the slope of those two lines, if you do a multiplication for the two lines slope, you will get the negative 1. That's a rule to determine if two lines are perpendicular. But he didn't tell us why. But that's fine. That's it. So this is today's video, and I'll see you guys in the next one. Bye.